Okay, I hope you can see the slide on irreversible reactions in parallel. So I was sorry yesterday I was not able to finish this particular part because there was a pop-up on my screen that that cannot be closed. So I need to do something with my computer, and I cannot have it restarted because I have a lot of things that I have done that I haven't saved. Anyway, so yesterday I was discussing regarding the parallel reactions, and this is our parallel reaction. And this particular parallel reaction can also be written in this form. Okay, this is just a review. So in your book, this is how actually it's written. So you have it written like that. And you have the corresponding rate constants here for the two competing reactions. Now we view the separate reactions that are simultaneous to be elementary. That's our primary assumption. And we write the net rate equation based on component A in this manner. So we account for the manner in which A is being consumed in the first and in the second reaction. The same way that we can write the rate of reaction based on component A, we can also express it in terms of components R and S, the products of the simultaneous reaction. And this time we have specified that our rate constants are expressed in terms of R and S. So we write it as positive. I'm referring to the rate of change of the concentration with respect to time because the R and the S are products. Now, if you're going to evaluate this net rate equation based on component A and separate variables, this would be your working equation. Okay. If you're going to get the ratio of the two reactions, rate of reactions in terms of the products R and S, this would be your equation, resulting equation. So the common variables, the common differentials are cancelled, giving us the remaining dCr over dCs equated to K sub R over K sub S. If dCr, dCs is separated, like transferring the dCs on the other side, then you can have it evaluated anyway. K sub R and K sub S are constants, and you will have this particular equation. Now, if you're going to have again or to use the graphical approach to the interpretation of the first equation that you are seeing here, if you're going to separate the ln's here based on the property of the ln, you will have a linearized equation. Now in the form, so if I'm going to write it here, your linearized equation, if I will transfer the negative in this side, or never mind, we'll just write it here. So you will have the ln of CaO over the ln of Ca to get rid of the negative. And you will have here K sub 1 plus K sub 2 times the time, which can further be written as, if I'll separate this, that would be ln of CaO minus the ln of Ca being equal to K sub 1 plus K sub 2. See, if we will linearize this particular equation, we will keep the ln of Ca in this side. So you will have this particular equation, negative ln of Ca equal to negative ln of CaO plus the quantity K sub 1 plus K sub 2 T. We want to make this positive, so we multiply everything by negative 1, the entire equation by negative 1. So you will have ln of Ca equal to, so this becomes negative now, plus ln of CaO. This one, when plotted, will be your y. This one, the t, will be your x. The quantity K sub 1 plus K sub 2, the negative of that will be the slope of the line. And the entire ln of CaO will be the y-intercept. So that's the reason why it's stated here that the first equation yields a plot. with a slope equal to the sum of k sub 1 plus k sub 2. Of course, it is negative. The last equation, referring to this one, yields a plot with slope k sub 1 over k sub 2. Though you see here, class, that your ratio of the rate constants are in terms of R and S, in terms of stoichiometry, if I will erase, in terms of stoichiometry here, you could see that if k sub 1 and k sub 2 are the rate constants based on component A, and k sub R and k sub S are the rate constants, of course, based on R and S, in terms of their stoichiometric relationship, it's just 1:1. So that's the reason why in this statement you have that the last equation yields a plot with slope k1 over k2, because this k sub R over k sub S is just equivalent to k1 and k2, even if you're going to go back to stoichiometry. Because the relationship between R and A, same thing with S and A, is just 1:1. So the rate constants are just the same for the two. Okay, the k sub R is k sub 1 and k sub S is equal to k sub 2. Now, if you solve these two equations, referring to this equation here and this equation here on top, that will help you solve for the rate constants of the two competing reactions. So solving the two equations simultaneously will determine the value of the rate constants k sub 1 and k sub 2, which happens to be the same as k sub R and k sub S. Because, as I've said, based on stoichiometry, they're just equal. Okay, so these are the equations. So primarily, we need to recall this equation. Actually, if you understand the principle, there's no need for you to memorize because you can easily have it derived. And this one, for parallel reactions. These are the two very important equations for parallel reactions in which the stoichiometry is like this. The one that was shown to you a while ago, here on the previous slide. Okay, now that's for parallel reactions or competing reactions. Now let's go to homogeneous catalyzed reactions. By the way, do you have any questions here? Okay, so there's none. So we go to homogeneous catalyzed reactions. So these are reactions that are said to be having the presence of the catalyst. Now it will, the reaction will proceed even if we don't have the catalyst in the first place. So the manner of solving problems like this would be, you have to write the stoichiometric equation without the presence of the catalyst. So let's say catalyst is C, represented by C. So this is your uncatalyzed reaction. The A forming R, wherein you have the rate constant K sub 1. Now, you have to write the same reaction with the presence this time of the catalyst. So you have A plus C forming R plus C with the rate constant K sub 2. So the catalyst, since it's not being consumed in the course of the reaction, you get to see it in both sides of your equation. So you have C on the left and you have C on the right. Now, when you write the rate expression, so you will have one rate expression or rate equation based on the uncatalyzed reaction and another one based on the catalyzed reaction. So you could see that you have now the concentration of the catalyst here represented by C sub C. So just like the competing reactions, we view this uncatalyzed and catalyzed reactions as elementary when we write the rate equation or when we write the rate law. Now, moving on, the reaction will proceed in this case even without the catalyst present, and the rate of the catalyzed reaction is directly proportional to the catalyst concentration. Now, this is related to this particular thing in here. So the rate of the reaction is directly proportional to the catalyst concentration. We increase the catalyst concentration, the rate of reaction, of course, increases. Even if we don't have this formula to show how the rate is depending on the concentration of the catalyst by virtue of the catalyst, which its purpose is to increase the rate of reaction. It follows that the more you have it in your system, the greater is the increase in the rate of the reaction. So that's where this particular principle is anchored on. But when we write the equation for this homogeneous catalyzed reaction, we have to consider both. We have to consider both the uncatalyzed and the catalyzed reaction. So it's just like you're writing the net rate equation, though you only have one reaction, but this time you consider the one which does not have the catalyst and the one that has the catalyst. Now, in the two terms that you have here on the right, you have C sub A, so that could be factored out. And you have K sub 1 plus K sub 2 C sub C multiplied to it. Now, this is easily evaluated using separation of variables. Okay? So if you separate variables, you will have negative ln of Ca over CaO for this one. And this one, of course, will yield K sub 1 plus K sub 2 times C sub C. Now, this whole thing will be multiplied to T, coming from the dt, which you transferred here on the right side. Now, this negative ln of 1 minus xa is the same as this one. So we have, or you can change the Ca here in terms of CaO 1 minus xa. So the CaO in the numerator gets cancelled with the CaO in the denominator, leaving you with a negative ln of 1 minus xa. So this one is just taken from this. So just another way of expressing the left side of the equation other than concentration. So if the problem gives you conversion, you can use this formula. If it's giving you concentration, you can give this particular formula. Now, this K sub 1 plus K sub 2 C sub C is referred to as, or is represented as K observed. That's the observable rate constant for your homogeneous catalyzed reaction. Now we move on. Now, how do we tackle problems concerning homogeneous catalyzed reactions? So we need first our empirical data. So making a series of runs at different catalyst concentrations will allow you to solve for K sub 1 and K sub 2. Just like if you recall the empirical rate equation in determining the N and the K, wherein you can perform a series of experiments starting at different initial concentrations, and then you determine the corresponding half-life or the corresponding fractional life based on those initial concentrations. In here, you make a series of runs at different catalyst concentrations. That way, you can solve for K sub 1 and K sub 2. So how is it accomplished graphically? So you plot the K observed against the catalyst concentration. Now, you may wonder why, where is this coming from? You plot the K observed against the catalyst concentration. So if you go back to the previous slide, you can see here that your K observed actually, or if I will just represent it as K sub O, is just one, the K sub 1 plus K sub 2 C sub C, right? K sub O, or K observed, is K sub 1 plus K sub 2 times C sub C. So in this case, if I go back in here and I'll write it in here, your K observed, which is K sub O, is just K sub 1 plus K sub 2 C sub C. Okay? Now, it says here, you plot the K observed against the catalyst concentration, you'll be able to get the values of the K sub 1 and K sub 2. How is that? So this is your Y, this is your X, this is your M, and this is your B. So for that line that you have plotted, the slope of the best fit line represents the rate constant for the catalyzed reaction, that is K sub 2, and the y-intercept represents the K sub 1, the rate constant for the uncatalyzed reaction. That is if you're going to do graphical. But even if you don't do graphical, given a set of data, a pair of data set, K sub O and C sub C. Your K sub O is the Y, and your C sub C is the X. Using linear regression in your calculator, you can get the slope of the best fit line and the y-intercept. So you right away can get the K sub 1 and the K sub 2. So that's the importance of knowing how to use linear regression in your calculators. Anyway, all calculators now, as long as it's scientific, have that capacity to do linear regression. Okay? So any questions so far? Okay, then we proceed. So after homogeneous catalyzed reactions, since we're talking about catalysts, we'll go to autocatalytic reactions. So what are these reactions? These are reactions in which the product has a catalytic, shall I say, catalytic effect on the reaction, or the product itself of the reaction acts as its catalyst. Okay, in this case, you write the reaction as originally, your reaction, by the way, is only written as a forming R. And since this R has a catalytic effect, meaning the more R that you have, the faster is the reaction because it has a catalytic effect. So you modify the manner of writing your original reaction of A forming R. Since R has a catalytic effect, then you place A plus R forming R plus R, denoting that this R here has a catalytic effect in your reaction. Now, if you're going to write the net rate equation, or shall I say the rate equation, because you only have a single reaction here, you have to account for the concentration of the product. You have to place it in there because it's also at the same time acting as a catalyst. So you have now K, C sub A, C sub R, if you express your reaction in terms of reactant A. Now, for this particular reaction, as long as stoichiometrically this is how it's written, the total amount of moles at any particular time should be a constant. So if you're starting with an initial concentration of AO and AR, or let's say CAO and CRO, then at any particular time, the sum of these two concentrations should be equated to also to the remaining amount of A and the final amount of R formed in your reaction. So you can see here that the sum of CAO and CRO is equated to CA and CR because it's a constant. Now, we need this very important equation because if you're going to process your rate expression here on top, it should only be expressed in terms of two variables. Those two variables are C sub A and time. And since you have C sub R, there's a need for you to find an expression for C sub R that is in terms of C sub A. And where will you get it? You will get it from here. So from this particular equation, you will have C sub R equal to, if the sum of the initial concentrations of A and R is represented as C sub O, then that would be C sub O minus C sub A. That will replace here the C sub R. Now, if you go further, this will be the resulting rate expression. Your C sub R is changed to C sub O minus C sub A. If you do separation of variables and process the integration portion using method of partial fractions, this will be the corresponding formula that you will be getting. Okay, so you will have an ln of, in terms of the initial concentration of A, and the total initial concentrations of A and R, and the remaining concentration of A. Or it could be expressed in terms of the final concentration of R and its initial concentration here, the ratio of, and in the denominator of the argument of the ln, you have CA over CAO. Now, these two expressions here in terms of ln can be equated to any of these two. Anyway, they are just the same. Okay, so this is your resulting equation after you did separation of variables and use method of partial fraction in integration. If M can be used to represent the ratio of the initial concentration of R and A, then this part here can be represented in terms of conversion. This equation that you have here are all in terms of concentration. So you are provided with an alternative equation on the left side to equate these expressions on the right if the problem gives you conversion. But actually, even if the problem gives you conversion, you can still find the CA using the XA. It's still CA equal to CaO times the quantity 1 minus XA. But nonetheless, if you want a ready-made formula to use, wherein you can plug in right away the value of the conversion and the M, then this is that particular formula. This is for the autocatalytic reaction. Now we move on for the very important things that we need to take note of regarding autocatalytic reactions. So for autocatalytic reactions, there is a requirement that some product R must be initially present if the reaction is to proceed at all. So meaning there should be a little amount of R initially present for the reaction to proceed. If not, there won't be any reaction that will happen. Now, unlike the homogeneous catalyzed reaction, that it would still happen without the presence of a catalyst. Now, the rate is expected to increase since this is autocatalytic as more R is formed. And when A, our reactant, is about to be used up or consumed totally, the rate drops to 0. The rate is maximum when concentration of A and R are said to be equal. So this is very important. When is the rate for an autocatalytic reaction maximum? It's when the concentration of A and R are equal. Now, again, another graphical approach to this, the plot of time and concentration for autocatalytic reactions yields a straight line passing through the origin. So if you're going to linearize your equation for this particular type of reaction, there won't be any y-intercept. So you only have a line which is in the form y is equal to mx with no b. That is why it said here, it's going to pass through the origin. And that's for the autocatalytic reactions. Do you have any questions so far? There's none. Do you have any questions? Okay, I think there's none. Okay, so we have here a sample problem regarding autocatalytic reaction. So the reaction that is given below is not the same in terms of the stoichiometric equation to the example that is given. I'd like to go to the form of the autocatalytic reaction. This one. Okay, it's not the same as this because you only have a single species A here and it's converted to R, and this R is said to have a catalytic effect, an autocatalytic effect. So for our sample problem, the reaction below is elementary and the product R has a catalytic effect. So this time, you are given two reacting species, and that's A and B. And your part of your products, or one of your products, that is R, is having a or has a catalytic effect. You're given this initial data, so initial concentration for A, B, and R, and at time equal to 10 minutes, the conversion is 40%, or that's 0.40. So you are to find the specific reaction rate, the concentration of A at which the reaction velocity is maximum, and the time when the reaction velocity is maximum. Okay? So I would like us to solve this problem and like to go to the Jamboard. That way we'll have lots of space to use for this particular, for the solution of this problem. So let's go to the Jamboard. Let me just open it for now. Okay, new share. Okay, so we're here now. So for our problem, let's take note of the given information so that we can base our solution to the given information. So for our problem, you're given the, wait kasi. You have this reaction A plus B forming R plus S. And then you're given the initial concentration of A and B being equal, and that's 2 moles per liter, and that of R is 0.10 moles per liter. It was noted that after 10 minutes, A is 40% converted. So our conversion is 40%. So it says here R has a catalytic effect. So meaning we have to redo the original reaction. We have to rewrite it. Now the specific reaction rate, so it's represented as specific reaction rate or SRR. This is actually the K, okay, the rate constant. And the concentration of A at which reaction velocity is maximum. So C sub A when the rate is maximum. And letter C, the time when the reaction velocity is maximum. So T when rate is also maximum. So these are the three information that we need to determine. The K, the C sub A, and the time when the rate is maximum. Okay, so let's go to our solution. So based on the concepts that we have covered regarding autocatalytic reactions just a few minutes ago, how will I write the new reaction for this autocatalytic reaction? Or how will I write the new stoichiometric equation? You can write on the chat box, or you may raise your answer here. How do I write the stoichiometric equation since R has a catalytic effect? A plus B plus R forming R plus S plus R. Very good. So that's the answer. So initially you have only A plus B on the left side. And since R has a catalytic effect, you write R. And you have here R plus S, and you have to account for this catalyst here, which is R. Okay, so that's your new stoichiometric equation. When you write the net rate, so I keep on saying net rate equation, we only have one. So if you write the rate equation, how should it be written? Or if I write the rate law, how should it be written? Anybody? You can write in the chat box. How should I write the rate law? How should I write the rate law? Aina, how should I write the rate law? Okay, I have the answer here already. Thank you, Via. So we write the rate law as K, C sub A, C sub B, C sub R. So two concentration terms should appear. Now remember that your unknown function is C sub A. So how am I going to simplify the expression on the right side? That way, I'll be able to evaluate this T. Any suggestion on how am I going to do that? How are we going to do that? You have three here, C sub A, C sub B, C sub R. We don't have any problem with C sub A because we already have C sub A there on the left. Our problem is with the C sub B and with the C sub R. What do we do? You have learned already that principle previously. It was covered. What would you do? Vincent Millares, any suggestion on what we're going to do on the right side?
Isaylo ng CA, miss.
What about the C sub B and the C sub R? What will you do with it? Patrick Tagle, what will you do with the C sub B and the C sub R?
Yung parentheses siya, miss.
Will express C sub B and C sub R in terms of C sub A. That should be the most simple thing that you can do. You cannot process your DE with the C sub B and the C sub R because your unknown function is C sub A. So you express C sub B and C sub R in terms of C sub A. We have discussed this already, that C sub BO can be expressed in terms of C sub B can be expressed in terms of C sub BO times the quantity 1 minus X sub B. And your C sub R can be expressed in terms of C sub C 0 minus C sub A minus C sub B. Or the simplest thing to do is this C sub A and this C sub B, actually this CO, you have it as a constant. Your C sub A and your C sub B are taken from this particular equation. I'll have this as equation 1 and go back to that. At any particular time in your reaction, the sum of the concentrations should be the same. So what I'm saying is this, CaO plus CbO plus CrO, which is equal to C sub O is equal to C sub A plus C sub B plus C sub C. Oh, sorry, C sub R. Do you follow? Okay, it was covered in the slides. At any particular time, the concentrations, the sum of the concentrations, initial and final, should be equal. So this is what I have written here. Your C sub R is equal to C sub O minus C sub A minus C sub B. Now then, we have to find a manner of expressing C sub B in terms of C sub A. That way, your C sub R now will be totally expressed in terms of C sub O and C sub A only. Now, we'll have this as our, so from here, this is where you got, you took the C sub O minus C sub A minus C sub B equal to C sub R from this particular part here in your equation. We'll make that as our equation 2. Now, by stoichiometry, we know that CaO XaO over 1 is equal to CbO XB over 1, which is equal to CrO XR over 1. Right? So your CbO XA or XB is equal to CaO XA. From the formula CbO minus CbO XB for your C sub B, your CbO is just equal to CaO as given here. And your CbO XB is just CaO XA. So I will have here CaOXA. So if you recall in our previous discussion, I mentioned that if we are starting with the same initial concentrations for a bimolecular reaction, automatically your C sub B will be equal to C sub A. Hi? So from here, this one can be changed to C sub A. So from 1, negative dCA dt is equal to K. This is your C sub A. This is your C sub B, which is C sub A. And you will have C sub O minus C sub A and C sub B, which is C sub A. I hope you can follow. So you have dCA dt equal to KCA squared. And you will have C sub O minus 2CA. Okay? Then you do separation of variables. So you have dCA over CA squared CO minus 2CA equal to, so we can place here the negative K dt. And we can use the given information in the problem that at t equal to 10 minutes, this is 10 minutes, you have 40% conversion of A. So if you have 40% conversion of A, CA then would be CaO 1 minus 0.4. With the CaO equal to 2. So we'll erase the CaO here so we can substitute values right away. This is equal to 2. So that would be a 2 times 0.6, and that's 1.2 mole per liter. Now we have concluded a while ago that your Ca and your Cb and your C sub R can all now be expressed in terms of Ca in this form. So what you do, you just paste in here the correct limits. So we start with an initial concentration of 2, a final concentration of 1.2, a time here of 0, initial, and then a time here of 10 minutes. Because we have the conversion there, 10 minutes. So with everything in here, you can process it using your calculator and determine the K value. Can you please solve for the K value? This is your integral. What's the answer? Your CO will simply be the sum of the initial concentrations here. So you have a 2, and a 0.1. So we'll place it in here. CO is CaO plus CbO plus CrO, which is 2 plus 2 plus 0.1. So that would be 4.1 for your CO. What's the answer? Why is it taking so long for you to solve? You can use your calculator. There's something wrong then. Why should it be a math error? It's just a simple integral which you need to place in your calculator. This should be x, this should be x squared, this should be 4.1 minus 2x. Let me check. Okay. So there was an error because I missed to place the 2 there. The answer should be, you should know this. You should know how to work your calculators in just 2 minutes, get the answer. If not, if in just in the process of encoding and using your calculator, you will have a great problem already, then you will really be lost in kinetics if that is the case. So you practice using your calculator, especially in the integral part. This is correct, Dexter. Thank you. It's not negative because the right side is already negative. So you divide it by negative 10. So your K will be 0.0479. What should be the set of units for this? For this K that we have, this is our rate law. This is your rate law. What should be the unit, the set of units for your K? No, that's not liter per mole per minute. What's the set of units for the K? No, it's not liter per mole per second. Look at the given units that we're working on. Thank you, Jericho. That's the correct answer, the answer of Jericho. I already repeatedly showed to you how to determine the units of the rate constant. It should be liter squared per mole squared per minute. You have a third order reaction. How do you determine the units of the rate constant? It should be per unit time times the unit for concentration raised to 1 minus n. That's the formula in determining the correct set of units for your rate constant. So for letter A, this is already our answer. the specific reaction rate, or simply the rate constant, is 0.0479 liters squared per mole squared per minute. Okay? Now we go to letter B. So for letter B, you are asked to determine the concentration when rate is maximum. How will you find this? The concentration of A when rate is maximum. Any suggestion? So I'll write the rate law here because we're talking of when rate is maximum. Originally, your rate law is like this. But now it could be written as, we have already the rate constant, so it should be 0.0479. You have C sub A. This is also C sub A, so this becomes squared. And C sub R is 4.1. C sub O minus 2 C sub A. Okay? It's in here. It's even the integral that we have evaluated. The C sub O is 4.1, so I have already placed it in here. Now I'll go back to the question. Find the concentration of A when rate is maximum. What tool you have learned already can you use here, especially you are determining the concentration of A when rate is maximum? A mathematical tool that you have learned in the past that you can use here. So a mathematical tool. What mathematical tool will help you find the concentration when rate is maximum? Optimization. If it's optimization, Drexel, what's the simplest tool that you can use if you want to optimize? Differentiation. What particular principle in differentiation will you use since you are optimizing? What principle, what concept in differentiation will you use since you are optimizing? Thank you for you, Jericho. It's maxima minima. So you recall your maxima minima in differential calculus. That's what you're going to use in here. In maxima minima, to save us some time in here, you are to get the derivative of one thing with respect to another and equate the derivative to 0. That way you will know the value of that thing when it is differentiated and equated to 0. You are getting there the maximum or the minimum value. In this case, you are to differentiate the rate in terms of concentration. I like to place the negative here because our rate is the one that is negative, not the derivative. So you place here the d of negative r sub a. That's it. Then you differentiate this one. So you have to use here power rule. Why? Because you have two expressions here. So you have the first term times the derivative of the second, which is minus 2. This one has a derivative of 0. This one has a derivative of minus 2 plus the second term times the derivative of the first. So the derivative of the first is 2CA. Okay? And just place here the continuation. You set this to 0. That's a principle you've learned in calculus regarding maxima minima. And this will also be right away taken from the right side because you can divide the entire expression by 0.0479. It would still be a 0 here on the left. So I'll have here minus 2CA squared. This one will become plus 2CA times 4.1. This is 4.1 plus, that's not minus, 4.1 minus 2CA. Since this is already 0, you will continue on the other page. The next page, you will have 2CA squared. When placed on the left would be positive. This one. And this one, I'll copy. It stays on the right side. 2CA times 4.1 minus 2CA. Let me check. Okay. You see that there's a CA here and a CA here, so you can cancel one CA. So this would be 1, and this is canceled here. And you have 2 CA. By the way, you can also cancel the 2. So these 2 can be canceled also. We'll take this one here. So what is left on the left side is just the CA. And on the right, this 2 is gone already. So you have 4.1 minus 2CA. Now you will have 3CA equal to 4.1. So your CA is equal to 4.1 divided by 3. 1.37. So it's 1.37. So this has the unit mole per liter. Okay, so this is for your letter B. Now we go to letter C. So letter C is asking for the time when rate is maximum. What would you do? It's asking for the time when rate is maximum. What will you do? Any suggestion? Time when rate is maximum. 2 minutes for time. You have this integral. Right? You place in here the R, the K. And you have here dt. So we start with an initial concentration of 2. What is the concentration when rate is maximum? It's 1.37. So you place here 1.37. Time here is 0, and you have here the time. So the right side would be 0.0472 t. So you will evaluate this integral here when the final concentration is 1.37, because that is the time when rate is maximum. Time is, I have an answer here, let's see, 8.72. Correct. So that's 8.72 minutes. So this is the time when rate is maximum using the concentration of A when rate is maximum. Do you get it? You have any questions? Okay, so if there aren't any questions, we will continue this on Monday. We will have one long quiz. Prepare for one long quiz on Thursday next week for whatever topic we will have covered already. So you have the remaining time to practice solving problems and comply with your problem sets. that needs to be submitted. I'll stop sharing now.